This is the quadratic formula. You were probably taught it as a result of completing the square, a clever and quick method, but full of seemingly arbitrary steps. But what if I told you there's a whole other version of the formula, one that doesn't require algebraic tricks or even coefficients to get to, that we can use to derive the standard formula? Imagine this instead. You're handed the graph of some function. You don't know its equation, but you do know what its derivative function looks like. Can you use this to figure out exactly where the original curve must cross the x-axis? And what does that have to do with the area of a triangle and trapezium, if anything? This might sound strange, but it turns out the quadratic formula is just a version of something more general and deeper, seeded from this line of reasoning. If you're ready, we're going to reason our way to it. It might just change the way you see quadratics forever. We'll begin by looking at a quadratic function graphically. There are three key points we'll focus on. Gamma, the stationary point where the gradient is 0. Alpha, one of the roots, this is the value we're trying to find an equation for. And beta, some other point on the curve where we know both the height and the gradient. Now, here's the big idea. Can we somehow reason our way to what alpha must be using these points? It might be a good idea to take a step down into the gradient function. After all, this graph can tell us a bit more about changes in the original curve. Here's the plan. We're going to use area, yes, area under the gradient curve, to deduce what alpha must be. Why area? Well, because of calculus, we know that the area under a gradient function between 2 points tells us exactly how much the original function changes height between those points. Let me expand a bit on this, because it's the key concept that will underpin our proof. Let's examine more closely what's happening as we travel along the x-axis under the gradient function from gamma to alpha. Firstly, remember that gamma is where the gradient is 0, which is why it lies on the x-axis. Now, as we travel from gamma, area begins to accumulate, and this represents the original function gaining some height, slowly making its way towards the x-axis. Eventually, it gains enough height to fully cross the x-axis, and it's this location we call the root. The location of this root is not arbitrary and can be calculated by mapping out the areas surrounding it and seeing what value of alpha satisfies both of them. So, let's do that. To make this easier to work with, let's shift our coordinate system so that gamma is at 0. This means the distance from gamma to alpha becomes just alpha, and the distance from gamma to beta becomes just beta. We'll keep this shift in mind and reintroduce gamma at the end. Now, look at the area from the origin to beta. It forms a triangle and trapezium split at alpha. Let's label the triangle's area N and the trapezium's area M. These two areas are our main tools. To unlock alpha, we'll need two distinct expressions for each, giving us two meaningful equations, both of which must be satisfied by alpha. Let's build these expressions. First, N. We can go with the obvious. The area of a triangle is half of the length times the height, which in this case is half of alpha by f prime alpha, the height. This is why we needed two equations, because there's actually two unknowns, alpha and f prime alpha. We don't know the value of the gradient at the root. We need another expression for n though. Looking at the whole triangle from 0 to beta, the total area is a half of beta by f prime beta. But we know that m makes up the other part, so we can be clever and just say that n equals the area of the big triangle minus m, or a half of beta by f prime beta minus m. Now for m, the trapezium. The area of a trapezium is half the sum of the parallel sides times the width. In our case, the two sides are just f prime alpha and f prime beta. The width is beta minus alpha, so m equals a half of f prime alpha plus f prime beta times their difference. So far, so good. But we have a small problem getting another expression for m. Using geometry, we've exhausted all combinations. It might be tempting to say m equals the big triangle minus the small triangle, but that's not distinct from our other second equation for n. So, what do we do? Well, this is where calculus comes in. If we zoom out and remember what alpha actually is, it's the point where the original function equals 0. So here's the magical insight. Think for a little about how what I said earlier about the area under the curve might apply to this situation. The area from alpha to beta gives us the exact change in the function's height over that interval. But since f of alpha is 0, the change is just f of beta. So simply, m equals f of beta. That's our final equation, and it ties everything together. Believe it or not, this is really the gist of the method, as these four expressions already encode the value of alpha, and therefore an equation for the root. We just have to rearrange it using some algebra and substitution to isolate alpha in terms of the others. I encourage you to pause the video and try to do this yourself. It's tricky algebra, but if you can do it, it's almost like discovering new math. If you don't want to follow the algebra, you can skip ahead about 90 seconds. First, let's substitute the bottom two equations into the above ones. Now we can progress the first equation, keeping in mind what n is equal to. First, we expand out the half. Then, the brackets. We can subtract f of beta from both sides. Then, multiply the whole equation by alpha. Afterwards, do some light shuffling of the terms to group the coefficients of alpha together. And in doing this, we see that based on the top right equation, these terms can actually cancel. This leaves us with a simpler equation, which we can expand out again based on the top right equation for n. After this, it's just to multiply the whole equation by 2 over f prime beta. And then finally, take the square root. But hold on, this is still in the shifted frame where gamma equals 0. To get the real equation, we need to shift back by replacing beta with beta minus gamma, and alpha with alpha minus gamma, and then move gamma to the right side. So our final formula becomes this. And there it is, a version of the quadratic formula that didn't rely on any algebraic tricks to get to, derived just from points on the graph. That's all well and good, but does it actually work? Let's test it against a random quadratic. Here we have a small segment of a quadratic that just includes its stationary point. And we don't know how the graph continues. But if it did, where would the root be? We can use our formula for this. Based on the notation of our formula, gamma is 1.5. And we can choose beta equals 2. Which means f of beta is 4. And the gradient, by looking at its tangent, is approximately -1. Plugging all these into our equation gives this, which simplifies to this, which is numerically equivalent to, at least in one of the values, 3.56. This looks right because it is exactly right. Believe it or not, this formula works for any value of beta. 0, 1000, you name it. Once you have the corresponding height and gradient and gamma, you've got the location of the root. But wait, any value of beta? What if we set beta equals 0? Though it might not look like that does much, it can give us a unique version of the formula. Let's say we had the equation for the general form of a function that could give us a curve like that, a quadratic. We know gamma because by definition, the gradient f prime x being 0 means that 2ax plus b equals 0, which means x, which is gamma, must be minus b over 2a. Also, if beta is 0, f of beta is just c, and f prime beta is b. With all this in our equation, we can do some light shuffling. Wait, this is starting to look really familiar. Would you look at that? The quadratic formula popped out. So you can kind of see, there's not just one quadratic formula. There's really many. And the typical one we use is just a special case where beta equals 0. I'd like to end this video in two parts, the first of which is a challenge to the audience. Could this method be used to simplify the current equations mathematicians have for cubics, or even quartics? If you can, it might garner some attention. Secondly, and more importantly, if there's one thing you remember from this video, I don't want it to be this formula. The real formula here is to think deeply about simple things. Maths is more connected than you think.